Hi everyone, in this video we'll learn about ways of detecting planets beyond our solar system. They don't emit light, so we have to use indirect techniques to figure out that they're there. And one of the main ones we use is the fact that they block light from the star that they're orbiting when they go around it, when they transit it. And they only block a little bit of that star's light. So if you can imagine this city in Singapore at night, you're looking at the city from the water and you can see the lights in the buildings are making the skyline in the image. Imagine yourself moving back from your vantage point on the water so that each building is a separate little blur of light and you can't even make out the individual windows of the building. And then imagine that someone in the building closes one of the windows halfway and therefore blocks some of the light coming from that one window in that big blur of building light. That's how sensitive our instruments need to be. That's about how much light is blocked when a planet transits in front of its star. So our instruments need to be very sensitive to catch that. There's one other way that we can tell that planets are there orbiting the stars far away, and that is because as they orbit those stars, they cause the star to wobble a little bit due to its gravitational attraction to the planet. So the star might wobble toward us, and then we would see that as a blue shift on the spectrum of that star, or it might move away from us when the planet is behind it, and we would be able to detect that on the spectrum as well. That's the second way of detecting planets as they orbit stars far away. We're going to talk about the first way in this video, which is called the transit method. One thing to notice is that the planet has to line up so that it passes between the star and us. If the planet is orbiting the star in a plane that's perpendicular to our line of sight, we have no way of knowing it's ever there. We can only detect it if it blocks some of the light from the star as viewed from the Earth. And then the next question is, well, how much of the star's light is it going to block? To answer this, let's consider Earth-like planets passing in front of Sun-like stars. And we'll need some radius data. So the radius of the Earth is 6.4 times 10 to the 6th meters. And the radius of the Sun is 7 times 10 to the 8th meters. So the Sun is about 100 times as big as the Earth. And we'll also recall the formula for the area of a circle, which is pi r squared. So when the Earth passes in front of the Sun, if an alien's looking at the sunlight and trying to detect whether there are planets orbiting our Sun, how sensitive does that alien's instruments need to be? Well, how much of the starlight does the Earth block when it goes around the Sun? We just take that ratio. So we say pi r squared, where r is the radius of the Earth, divided by pi r squared, where r is the radius of the Sun. That's the fraction of the Sun's light that is blocked when the Earth passes in front of it. And because we're all friends here, let's make this easy on ourselves and just say that 6.4 is pretty much 7. So we can cancel out both the pi and the 7s. We're just left with 10 to the 6th squared divided by 10 to the 8th squared. And that's going to give us 10 to the 12th divided by 10 to the 16th, which will be 10 to the 4th in the denominator there, because 10 to the 12th divided by 10 to the 16th is in the denominator. So we have 1/10,000th of the light from the Sun is blocked when the Earth goes in front of it. And that doesn't depend on how far away from the Sun the Earth is. This fraction is going to be the same whether the Earth is close to the Sun, like kind of at the distance of Mercury, or whether the Earth is far away from the Sun. Those aliens are going to see that same amount of that same fraction of the starlight blocked as the Earth passes in front of the star. So 1/10,000th. Well, so then why are exoplanets that are closer to their stars easier to detect? This question brings us back to Kepler's third law. The ones that are closer in are going to have shorter periods because remember, closer, faster, farther, slower. The planets that are closer are moving faster, orbiting more quickly, and we'll see more dips in the starlight. We haven't had Kepler up there for very long. And in the time that it's been up there, you need 3 transits of an exoplanet to confirm that it actually exists. You can't just say that if you see a dip in the starlight, you're sure there's an exoplanet. It might have flickered for some other reason. So you need to see 3 periodic transits. You need to be able to predict the 4th one. And so if the period of a planet orbiting its star is on the order of many years, well, we wouldn't have had time to confirm that yet. So we've only been able to confirm the ones that are closer in. Let's look at a typical light curve from a star, and you can tell that if you see these dips, which have been greatly exaggerated, you can immediately see that there are 3 planets orbiting this star. The purple one's the biggest because it blocks more of the star's light. This is relative brightness of the star compared to 1 for when there are no planets blocking it. Then when this purple planet goes by, it blocks 0.01 fraction of the star's light. So we can tell that it's kind of a bigger planet. Over here, the blue one is blocking less than that, and the orange one is the littlest planet of all, blocking only a little bit of the star's light. So could we tell other things? Well, we can tell the period of each of these planets' orbits. We could tell that the purple guy has the longest period, and therefore by Kepler's 3rd law, we can infer that it's farther away from the star than the other 2 planets that are orbiting it. How much farther away? We can actually calculate that if we know the mass of the star. So remember Kepler's 3rd law, that if we have the square of the period divided by the cube of the radius, where the period's in Earth years and the radius of the orbit is in astronomical units, 1 astronomical unit being the distance between the Earth and the Sun, then that ratio is equal to 1 over m, where m is the number of solar masses. So m would be 6 if we're dealing with a star that has 6 times the mass of our Sun, for example. So if we do this, we can actually solve for what the distance of the star from its planet is. We can actually solve for r because we can see p right here on this light curve. We can see the period on the light curve, so we can calculate the distance of the planet away from its star, as long as we know the mass of the star. Really powerful technique to learn about worlds outside of our solar system. Thanks for watching.